So that's about it for the what do you call this? The space weather stuff. Now let me give you a little bit of a tutorial here on ionospheric conditions. I was asked to give a little bit of a tutorial about propagation in the ionosphere. I'm trying to align the camera, so hopefully you guys, I don't know if you can read the text, but don't worry, that's I'll go over all that. This is a tutorial to kind of give you a refresher on what the ionosphere is and all the different layers of propagation that you can see, and basically how space weather affects it. Hopefully this will kind of give you guys a little bit better feel for some of the things that I'm talking about and the types of space weather events that will affect you and how they affect the propagation. So to just start off, to remind you that the ionosphere is basically a charged region that's basically the upper atmosphere. It would be neutral, except for the fact that the sun's ultraviolet light charges it. And that is very nice because it now gives you like this sea of electrons that then can carry currents and carry charge anywhere it pretty much wants to. And that facilitates radio propagation. Without it, we really wouldn't be able to do any DX or anything like that. So that's really the basics idea of the ionosphere, but I'm sure all of you know that there are more than just one layer of ionosphere. There's actually multiple layers. And people ask me all the time, well, why? What do these layers mean? And let me try to see if I can close this so that you don't get distracted here. Maybe that's even more distracting, I don't know. So what I've got here is a picture of the ionosphere during the daytime and during the nighttime. And what I was talking about is electron density. So, basically what causes the ionosphere to actually allow propagation is that you actually are ionizing, you're actually ripping the electrons right off of these neutral atoms. So the sun is doing this through something called photoionization. So it's literally tearing off these electrons right off the atoms. And the atoms, of course, at the same time are trying to get them back. And basically whoever is winning that fight at one particular time depends upon the layer that you're in, the altitude that you're at. And what you're looking at here is, let's take just the day side, for instance. You're looking at electron density, and it goes up as you move to the right. And it goes up in altitude as we go up the screen here. So when you look at the D region, you really don't have a lot of electron density. I'm looking at this black line that goes up. But as you continue to go up in altitude, the sun begins to really strip off these electrons. And the neutral atoms are trying to fight to get it back. But at some point, depending upon the atmospheric chemistry and what species of atoms are in at that particular altitude, there's a balance. There's a peak. There's a peak at which the sun is doing the best job. It's winning the fight. And then as you continue to go up in altitude, because of just a particular kind of atmospheric chemistry, certain species are more prevalent than others, and they'll start losing the battle again as again situations change as you go up in altitude. So as you see these peaks, these little humps, they are actually the layers of the atmosphere, of the ionosphere. So you've got the sporadic E and the E layer that's about 100 kilometers. You've got an F1 layer that's sitting at about 200 kilometers and an F2 layer that's sitting at about 300 kilometers during the day. Now at nighttime, things simplify quite a bit because now you no longer have the sun trying to tear nonetheless. So what happens is that you've got an F1 layer and the F2 layer. They actually collapse into a single F layer. Again, the atmospheric chemistry that's going on, this little tug of war of electrons is changing. So you only have one peak here. And then down in here, the D layer disappears, and the E layer is not quite as strong. It's kind of sporadic, meaning you get peaks and valleys a little bit here and there, but it's not really a consistent layer all the way across. So you do have two totally different conditions here, and from the daytime to the nighttime. And when you try to think about, okay, how does that work globally? What does that mean? If I were to try to picture it around the globe, if I can get my mouse, what are we actually really dealing with? So if you take those layers and you wrap them around the globe, you kind of begin to get a visual picture of how this is being affected and what's really happening. So you've got the day side of the Earth, and you've got your four layers, your F1 or F2, F1, E, and D layers sitting here. But then at nighttime, the picture gets very, very simplified. The F layers collapse into a single F layer, and both the E and D regions pretty much disappear. But what's interesting is this region right in here. This is just right after the terminator, and it's really a whole region that's just entering Earth, basically Earth's shadow, where the sun, the Earth is actually shadowing out the sunlight from the upper part of this atmosphere. And you notice as the layers fade out here, it's not happening all at once. It's not just at the terminator. It's actually a broad region in which this happens. And there's an amazing amount of change that's going on all at once. You get conductivity changing, you get layers coming in and out, and they're all kind of collapsing all at once. But it's not just a light switch. It's kind of a fade. So this region is actually a third kind of region for considering what type of space weather effects and what type of ionospheric propagation you're going to get. So you not just have day, you don't just have night, you have day, night, and what we call the gray line or the gray region. And I'll talk about this a little bit more. So when you think about it from a global perspective, when you're doing DX and you're doing, and I don't see this highlighted enough when I look at some of these texts talking about radio propagation in the ionosphere. What they don't talk about so much is that it's so important to know when you are, not just where you are in the globe, but when you are. And that is also really critical when it comes to space weather as well, because things are ordered by a local time, and in space weather, they're actually ordered by something what we call magnetic local time, which adds the effect of the magnetic field into all of this change. So let me now kind of talk about the layers and really what type of propagation do you expect to get. Now what I've done is we've got the sunlit layer here, we've got the nighttime here, and we've also got this area here that's kind of showing the gray region. So these are the three regions that we need to talk about. Now you can see with the D layer, we kind of simplified it. We've only got one of the F layers here. Here's the E layer and then the D layer down here. Now during the daytime, your 60, 80, and 160 meter bands, forget it. The D layer pretty much absorbs them all, so you're going to have a hard time ever trying to use them during the daytime. Your 30 and 40 meter, bands, however, will refract off the E layer or reflect off the E layer, and you can get some good propagation there. Also, the 10 to the 20 meter band that will reflect off of the F layer. Now, when you get to this gray line, things begin to change. Suddenly that 60, 80, and 160 meter bands, those things actually will begin to propagate off the F layer, which is wonderful because during the day they weren't really working. But that gives you an idea that in the gray line, you start getting these interesting propagation effects. Now, granted, the F layer as well as the E layer, they're not gone. I mean, the E layer hasn't totally disappeared yet, and even some of the D layer hasn't disappeared yet, but you'll get holes, and you'll get the E layer changing as well as the F layer changing. They're collapsing. So this is where you get some magic, where you get some really interesting and very difficult to predict effects when it comes to propagation. Now, at night, you can get the F layer is a lot lower, so you can get some decent propagation on, let's say, 60 and 80 meters, hitting the F layer as well as your 30 and 40 meter band. And then, of course, your 10 to 20 meter band goes right through the F layer. So hopefully that gives you an idea. But the take home here is that really to know if you're going to be talking about your skip, your skip and MUF and all of that kind of stuff, realize that it's not just, of course, one area. It's not just day. It's not just night. It's three separate areas. All of this is going to change. Even if your MUF is the same, you're still going to have different skip distances and other things like that. So it really matters where you are. And again, this is really imperative when it comes to space weather as well. Now, I'm going to complicate this picture more by not just saying that these layers are just nice straight curves. Now we're going to talk a little bit about what happens when you add space weather into the mix. So let's talk about the D region, E region, and F region again. This is kind of just a cartoon, but it gives you an idea of what space weather really does to you. What happens now is that when you put this into reality, you take it away from the models and you do it for real. Now what happens is that these beautiful flat surfaces, these flat layers, suddenly become warped. You have things like atmospheric heating instabilities that come up from below and push parts of the ionosphere up so it bends the layers. You get waves in neutral and charged regions that then can cause conductivity changes and all this kind of stuff. So now your signal is no longer looking at a plain mirror. It's now looking at something that's rippled, like dropping a stone into a pond of water and watching the ripples. Imagine that being your F layer now. And now you got to bounce a signal off that. And where does it go? I mean, when you think about it, it's kind of like the difference between looking at a regular mirror and looking at yourself in a funhouse mirror. You have no idea what you're going to get. And that's what space weather really can do to you. And on top of that, now if it's not bad enough to have to deal with rippled layers, now you also have things like signal refraction, because what will happen is that you'll get some space weather effect that will change what we call the conductivity, basically the amount of electrons in part of a layer. And when that happens, suddenly you get the same effect that you get when you stick a pencil in water. At the interface of the pencil in the water, it looks like the pencil is bent. Have you ever seen that? You just dip it in there and it looks like it's bending like this. Well, it's the same kind of thing. You get this refraction. So now your signal that you're transmitting is now no longer going in straight lines. It's actually bending at this change in conductivity because it actually changes the index of refraction for that signal. So that's a space weather effect. And we have this problem all the time with GPS giving the wrong answer because of these signal refractions. Now imagine currents in charged regions. This is things like aurora or which cause things like signal scintillation. What happens there is you actually have currents. I mean, you saw that picture of the aurora. Those are actually currents going through the ionosphere. And when you have that, now think of a whole bunch of tiny little ripples on the water. And your signal, instead of just bending and refracting, now it scatters on all sorts of different directions. And that scattering can change. So you're looking at a signal that's doing this. And some of these signals can get out of phase and then destructively interfere. And that's when you get on the bands and you hear this weird modulation, and you hear the signal fades and comb filtering. If you're an audio engineer, you know what that means. You hear all these weird types of EQ, like somebody's playing with the EQ on your audio rig, and so you can get these types of problems, and we call that scintillation. And if you want a visual metaphor for this, just look up at the night sky, on a clear night, and take a look at the stars. You ever see them twinkle? When they twinkle, did you know? That is visual scintillation. Those are light waves that are scintillating. So basically in ham radio, you hear the twinkle, twinkle, little star. So I'll bet you never sing the song the same way again. That's what I've mentioned to people before. So that signal scintillation can give you things like signal fade and the phase modulations I'm talking about. Now, all of this is going on all at the same time that you're dealing with just the problems and the complexities of all these different layers. So you can imagine when people say that, why isn't my model working, or why is DX so hard and so unpredictable? Well, it's because there's so many different facets to it that are really hard to control and really hard to understand at any one time. And here's an example. I'll just show this very quickly. I know I'm probably running out of time. But here's a model of the world you can see right here. And this is just for the D layer. And what we've got going on, this is the daytime, this is where local noon is right here, but we had a solar flare and it really lights up the whole atmosphere, causes major radio noise, as you all know. This is a particle radiation storm that lit up the whole northern and southern pole. And then here is the gray line. As you can see, there's a lot of color changes, and it's not just one line, it's a very broad band. And so when you look at maps like this, like the D map here, or DRAP map, that kind of gives you an idea of what's happening in terms of absorption of your HF frequencies. You don't just look at where it's all red. I mean, red is bad, granted, but if you really want to know what's interesting, look at where the color changes rapidly. So right across here from purple to red, that's a big change across there. That means a ton of conductivity is changing, and that's where the magic happens. And it would happen here, and it would happen here. Anywhere you see these colors changing very rapidly. So that's why with these types of conductivity changes, that's why it can be a very, very complicated thing, but it also can be very magical. And I think, do I have any time left? Because if I do, I'll talk about this. But if not, I can save this particular thing for later. It's talking about KP, AP, and X-ray flux and how you can use those to help you understand what the space weather is doing. And I don't know, do we need to throw everything back?
I'm not sure where we are in time because we kind of got started out of sequence. Victor probably has more of a handle on time, but I think people are finding this so fascinating. I would say continue. I mean, this is great.
Oh, good. Okay. So yeah. Okay. So to talk about this last little bit, I know I threw a lot of stuff at you all at once. It's kind of like drinking from a fire hose, but I'll give you a last little bit here that might be able to give you some help. When you look at some of these solar indices and these space weather indices and you think, God, aren't they all don't they have just one index that I can look at that tells me everything? I hate to tell you this, the answer is no. But I'll talk a little bit about the most popular indices and really what they mean and what they don't mean. The biggest thing we see are KP, AP, or K and A, and then people look at either the X-ray flux or they look at the F10.7 flux to try to understand what space weather is doing and how it's going to affect radio propagation. And all I can say is that KP and AP do totally different things compared to the X-ray flux and F10.7, and I'll go into that now. KP is pretty much my go-to index for, or what I would say is a simple go-to index for things like solar storms. This is these are things that cause aurora. These are the big geomagnetic storms. And this is actually the KP index over the last week from basically September 1st all the way through today. And you can see, this is what I was talking about earlier with the space weather. We had an absolutely monstrous set of solar storming that just was almost nonstop, simply because of that big coronal hole gave us so much fast wind. We had tons of active conditions being yellow. Storm conditions is anything that's red. We had what we call a KP of 6, which was really bad storm conditions. But then we had little pockets of green. See that each one of these bars is about 3 hours, or is 3 hours. It's a 3-hour average. So we'd have 3 hours here, 6 hours here, that kind of thing. And then we'd storm for a long time. And then things are now beginning to finally settle down. Now, what's useful about the KP index is that even though it's a little bit behind, because they have to wait for 3 hours before they average it all together and then put out a number. So it does lag real time just a little bit. So it's not good for things like aurora, but it's okay for radio because the ionosphere takes a little while to respond as well. But what's good about KP is that if you want to get on the bands for 6 hours, let's say, you actually might be very interested in this period here. So the KP index will tell you, hey, you might actually get some marginal radio propagation during this small window, okay? And then, you might get another window here that's a little bit longer. Here's about 12 hours, right? So, you can actually use KP to kind of help you along, as long as you just pay attention to the green and leave away the yellow and the red. But if you use the AP index, it's simply a kind of a summation of what's going on with KP. The AP index has 1 bar for each day. Now, it's a slightly different scale. These scales go from basically 0 to 9, and the AP index goes from 0 to 100, essentially. But nonetheless, it's still color-coded if you go to NOAA, to the SWPC website, and you still get a decent idea of what the codes are and what is active conditions and storming conditions compared to good conditions. But the problem is if I just use the AP index, which gives you 1 basically value per day, then I would say basically September 2nd, 3rd, 4th, and 5th, I wouldn't have been able to get on the bands at all. Forget it. Just hang it up. It's over. But actually, if you go back to KP, no, that's not true. You had a 3-hour band here. You had 6 hours here, another 3 hours, and you actually had some time a little bit in here. So you actually don't get as much information from AP. And I don't use it. It's good for scientists who are looking for long-term trends or for climatology. But for weather, it just doesn't give you enough information. So if you had a choice, try KP, okay? Now, looking at X-ray flux and F10.7, this is a totally different ballpark. And this is the thing that I know always confuses people, is because I see it over and over and over again. People say, well, as soon as there's an X-ray, a flare in the X-ray flux, KP will immediately jump high. And it's like, no, that doesn't happen. Sometimes it doesn't happen at all. And sometimes KP will jump when there's not been an X-ray flare at all, as you can see in this case. This is the same period, September 1st all the way to September 8th. Same period as here. This is the M-flare threat meter, this line, or M-flare threat level, this line right here. And as you can see, we are well below that. We haven't even popped any C-class flares. So this is radio quiet. And yet KP is all over the place. So what we're talking about here are 2 totally different phenomena. And that's why it's so important that you have to look at both. X-ray flux and F10.7 tells you about radio propagation in terms of ultraviolet light hitting the ionosphere and lighting up the ionosphere either enough for radio propagation or giving you so much with an X-ray flare that you end up drowning out any radio propagation because the sun is making all the radio noise. So that's what this tells you. This is all about light. These, KP index is all about geomagnetic storms, big, massive burps and belches from the sun that carry particles and magnetic field to the Earth that are slow and slam into the Earth and cause aurora. 2 totally different things. So really, when it comes right down to it, if you want to look at indices, KP is a great one, and even just looking at the GOES X-ray flux, that's a great one too, because you can see where the flares are, and you can kind of see where our solar flux levels are. And if they get to about the B level down here, you're going to start kind of worrying about radio propagation. As long as they're in between B and C, radio propagation should be pretty marginal, if not okay. So hopefully that helps kind of give you guys a little bit more feel for what indices to use when you look at NOAA and what they're for and why you have to look at all of them. Back to you, Val.
Oh, that was wonderful. And it was really nice putting a good visual on something that we probably had to memorize to get our ticket. So it really made it easy. And what's the website you go to for a lot of that? What website do you use?
The official website is the NOAA SWPC website. I think I may get this wrong, but it's www. As a matter of fact, I can look it up. Hold on one second. Let me pull up I don't want to give you the wrong one. So it's www.swpc, which is swpc.noaa.gov. I don't know if you can see that. Probably not.
Okay.
swpc.noaa.gov. And that gives you basically all of the space weather information and all these indices. It's a little bit thick to get through, but you can hunt for them and you can find them. And especially for radio propagation, they actually have a dashboard, what they call a dashboard for radio propagation, and that will get you started.